Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 23, 2025, about 2 days ago. The big result is that this paper introduces NCCLX, a communication stack that cuts steady-step Llama 4 training latency by up to 12% and speeds training startup at 96,000 GPUs by up to 11 times, while also slashing distributed inference latency by 15 to 80%. The paper is titled Collective Communication for 100K plus GPUs, and as we'll see later, the implications for model training are quite significant. Beyond speed, the system reduces GPU memory use, supports dynamic patterns like mixture of experts, and improves reliability at 100,000 scale. Alright, Table 1 organizes the landscape by phase, linking unique problems to the features that address them. The left phase column groups rows as generic, training, multi-node inference, control plane, and tooling. The generic phase highlights host-driven customization and zero-copy data transfer, which reduce interference and congestion across diverse patterns. Training phases map to zero-copy and SM-free send-receive, RMA put, and fault-tolerant all reduced to improve overlap and resilience. Multi-node inference gains GPU-resident collectives and low-latency optimizations, while control plane and tooling cover scalable initialization, resource management, and fault localization. So, while Table 1 grouped phases and features, Figure 1 maps the multi-building network that makes 100,000 plus GPUs act like one fabric. The diagram shows each building split into 8 AI zones, feeding an aggregator training switch layer, which then connects across buildings through a fully connected mesh. This mesh keeps cross-building traffic comparable to cross-zone traffic, so latency mainly depends on hop count. The layout highlights scalable growth by adding buildings without redesigning topology. So the previous figure mapped the network fabric and its latency tiers. Figure 2 shows the communication stack that sits under PyTorch, unifying host-initiated with GPU-resident metadata, and device-initiated modes. The right box highlights the host-driven framework with the C-tran transport, which enables zero-copy and SM-free transfer, topology-aware routing, and custom features like remote memory access and fault tolerance. The left box contrasts the baseline kernel-driven path that relies on copy-based transfer. Well, Figure 6 presents the DQPLB design that tames zero-copy bursts by pacing traffic. Panel A outlines a control queue pair for address exchange and multiple data queue pairs that carry payloads across the fabric. Panel B illustrates segmentation and limits. Messages are spread round-robin across 4 data queue pairs, capped by per-pair outstanding counts, and a maximum segment size. Ordered delivery holds, because sequence numbers and completions gate further sends. Alright, Figure 7 benchmarks point-to-point transfers and compares zero-copy sends with the copy-based baseline. The left panel shows normalized latency across cross-host, cross-rack, and cross-zone links, and zero-copy stays near 1 while copy adds a constant tax that can nearly double delay. The right panel reports bandwidth versus data size, where zero-copy reaches the top line, but copy lags on medium sizes even with tuning. Alright, Figure 7 highlighted point-to-point wins. Table 3 reports end-to-end decode latency for token shuffling with all-to-all V dynamic. Single node shows up to 43% faster decode at k equals 1, with little change at k equals 4. Distributed inference sees larger gains because communication dominates, reaching about 19 to 83% across batch sizes and host counts. Gains grow with larger k and with more hosts, which increase the data moved. Alright, while Table 3 quantified decode gains, Figure 21 shows default process group initialization time across 8,000, 32,000, and 96,000 GPUs. The bars indicate baseline took about 15, 56, and 265 seconds, whereas NCCLX needed roughly 4, 12, and 24 seconds. That gap reaches around 11 times at 96,000 GPUs, which matters because frequent restarts otherwise stall training. These savings come from scalable bootstrap and on-demand connections that avoid all-to-all setup. Okay, 2 takeaways stand out. A host-driven, zero-copy transport in NCCLX cuts training and inference latency meaningfully, and scalable initialization plus resource trims make 100,000 plus GPU clusters practical day-to-day. The broader implication is faster, more elastic Llama scale systems. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.